All right, class, you finally arrived. You're going to finally be doing some actual real statistics. So chapter 10 is all about what we call hypothesis testing. And hypothesis testing is doing what we do in science. So we use data to form hypotheses. Sorry, we form a hypothesis and then we use data to test that hypothesis and come to a conclusion. That's what science is all about. And statistics is really the main tool that we use in science to verify the strength of our conclusions. Okay, so this whole chapter, chapter 10, or at least what we're going to be covering from chapter 10, is all about how to use statistics to verify the strength of our conclusions as researchers, as scientists. So let's lay the groundwork here. So first definition, an hypothesis is a statement regarding a characteristic of one or more populations. All right, so a characteristic of a population. There's one main characteristic that we're interested in, which is parameters. So as statisticians, the characteristic of populations that we're interested in are parameters. What is hypothesis testing? Hypothesis testing is a procedure using sample data and probability to test statements of an hypothesis. So pretty much everything that we've done so far, the descriptive statistics of chapters 1 through 5, I believe, the probability that we use to assign likelihoods to certain outcomes. And now hypothesis testing, which marries these two things together into what we're finally doing is inferential statistics. So we're drawing inferences. And remember, when making an inference, you never know completely whether your inference is true. And so when you're in the realm of, when you're dealing with things that aren't completely true, then you're dealing with probability, you're dealing with likelihood, and ultimately you're dealing with inferential statistics. Okay, so this first section is about getting you some of the vocabulary and the basic conceptual framework for hypothesis testing. So some of this is going to kind of come out of left field, but we're laying a groundwork, and you really just need to be exposed to it at first and start getting a sense of how some of this language works. Okay, so hypothesis testing from a student's standpoint involves the evaluation of a particular claim that's made by a researcher and determining whether that claim is valid or not. So there are two main claims that a researcher can make. Those two claims in this context are the null hypothesis, which we denote H sub 0, and we say H naught. This is the null hypothesis. We'll explain what this is. Or the alternative hypothesis, H1. Okay, so these are the two claims that a researcher can make. Okay, now, as it turns out, there are two claims because H0 and H1 are always complementary. They always fill in complete each other. So either we claim one thing or we claim the exact opposite. There is no claim, third claim that can be made. So let's look at an example of what this will look like for us in statistics. So there are two main flavors of claims that can be made, and depending on those, the flavor of claim that's being made, we either have what we call a two-tailed test or a one-tailed test. Okay, so this is what that looks like. The first flavor is the two-tailed test, and here the null hypothesis would look something like a parameter equals a specific value. parameter equals a specific value. And the alternative hypothesis would be the opposite of the null hypothesis, which would be the parameter does not equal that value. So these are the two claims that a researcher might make in this two-tailed flavor of test. So an example might be a researcher might say mu equals 1. Okay, this mu equals 1 would be the null hypothesis. It has equality. That equality is what the null hypothesis is all about. It has equality. So they may claim that mu equals 1, or they may claim that mu does not equal 1. And if they say it does not equal 1, then either mu is greater or mu is less than 1. And so it's either in the left tail or the right tail. So that's why we call it a two-tailed test. So we know that the sampling distribution for mu is approximately normal. This would be based on sample data. And so we know that when we compare our sample to our x bar to the mu, either x bar could equal mu, which equaling mu in a statistical way means close enough to mu to say it's equal, right? Not exactly equal. It's a little fuzzy there. Or our sampling statistic, x bar, could be not equal to mu, in which case x bar would fall in one of these tails. So that's why we call it a two-tailed test. Now, we could also make another flavor of claim, which we call which is a purview of one-tailed tests. So here our null hypothesis would be a parameter is less than or equal to a value or greater than or equal to a value. The alternative hypothesis would be the opposite of these, which would be for less than or equal to, the parameter would be strictly greater than. For greater than or equal to, the parameter would be strictly less than. So the alternative hypothesis always opposite the null hypothesis. The main thing to always notice about the null hypotheses is that they always have some sense of equality. So here in the two-tailed test, the null hypothesis has an equation sign. Here in the one-tailed test, it's a less than or equals to, greater than or equals to, right? And in some cases, the book may completely ignore the less than and just say H0 is equal to, H0 is the parameter is equal to, even in the one-tailed case. So it depends on the resource, it depends on the book, but the way that I was taught is the null hypothesis is always for one-tailed test, it's a less than or equal to or a greater than or equal to, not a strictly equals to. That is reserved for two-tailed tests. But the book may do it this way. So be careful, don't get confused by that necessarily. Okay, so one-tailed tests, we are expanding the kind of range of what the null hypothesis could be. So here, for this particular example, we might test the claim that our parameter is less than or equal to a certain value. So again, we could make it 1, or our parameter is strictly greater than that value. And so this would be your null hypothesis over here, and this would be your alternative hypothesis over there. And you can see that we are testing only one tail. So that's why I call it a one-tailed test, because the alternative hypothesis only occupies one tail, whereas in the two-tailed, the alternative hypothesis occupies both tails. So that's why we call them one-tailed versus two-tailed tests. This whole image could be flipped around, and you could get the other variation on H0 and H1 for one-tailed tests, where the where the one-tailed alternative hypothesis would be on the left and this would be on the right. Okay, so that's a lot of information, and you're going to get more familiar with this as you actually start solving problems in this hypothesis testing chapter. So this, again, a lot of what you're going to see right now may feel like it's coming out of left field, that it's not very well motivated, but we're just trying to lay the groundwork so that when we start using this language in the next section and we're doing actual problems, you won't be completely lost. Okay, so these are two-tailed tests and one-tailed tests. The H0s and the H1s always come in pairs that are complementary. All right, so let's look at an example. So when you're doing these problems, they're going to be word problems, like a lot of the statistics stuff is. And I can't go over every possible variation on a word problem. It would take too much time. So I have to try to do this in as succinct a way as I can. So this example, I'm going to show you two things that you might read within a problem. And depending on what you read, you're going to be told explicitly either who the alternative hypothesis is or who the null hypothesis is. Okay, so we're reading a problem, and in the problem it says the proportion of individuals taking the new drugs who experience a headache as a side effect is 0.02. So the way this might actually be read is the researchers are testing the claim that the proportion of individuals taking the new drugs who experience a headache as a side effect is 0.02. Okay, so they'll tell you explicitly in this case who H0 is. H0 is the proportion is 0.02. So you have equality, right? Now, one thing that's important here is, well, before I move on, the proportion is 0.02. So is functioning as an equal sign. They're telling us what H0 is here. H0 is P is equal to 0.02. Okay, now I'll stress this over and over again because this is where people get confused. If you read it in the problem, then whatever you're reading, generally speaking, is the claim that the researchers are making. So I didn't write it all out in words, but I could say the researchers claim that the proportion of individuals taking the new drugs who experience a headache as a side effect is 0.02. So not only are we being told what the null hypothesis is, but we're also being told what the claim is. So the researchers are claiming this to be true. They don't have to claim that to be true, but we're being told who the claim is. Alternatively, they could say the researchers claim that the proportion of individuals taking the new drugs who experience a headache is more than 0.02. The proportion is more than 0.02. So they've told us what the alternative hypothesis is more than is a greater than symbol. So we know that there is no sense of equality here. They don't say at least 0.02. They say more than 0.02. So if it was at least, then you would be able to put a little equation line here, and then you would know that this would actually be the null hypothesis. But because it's a strictly more than, which means it's strictly greater than, it's definitely the alternative hypothesis. And again, since it's the thing that you see, this in this case, the researchers are claiming that the alternative hypothesis is true. So you always have a null hypothesis, you always have an alternative hypothesis, and as a researcher, you can claim one or the other. Okay, so researchers can claim either H0 is true or H1 is true. Depending on which one is the claim for the researchers, they can reach different conclusions. Okay, so we can claim H0 or H1. Depending on who we claim, we'll get different results. So there are two types of errors that we can make when reaching conclusions about claims that we've made, right? So we have an H0 hypothesis and an H1 hypothesis. We can claim either H0 or H1 is true. We then use data to determine which one of those is true, and then we reach a conclusion. Now we can reach valid conclusions based on the data, or we can reach invalid conclusions. So this table here breaks down the various ways that you can, the various arrangements of truth and conclusion and whether you have an error or not. So first, we could say H0 is true. So the null hypothesis is actually true. Then there are two conclusions we can make. We can say we do not reject the null hypothesis, meaning we do not say that the null hypothesis is false. So we know H0 is true. The conclusion we could reach is either reject H0 or don't reject H0. These are always the conclusions that we notice. There is no reject H1, don't reject H1. Those aren't possible conclusions. Conclusions are either don't reject the null hypothesis or reject the null hypothesis. Now, if we know H0 is true, if we determine H0 to be true in a statistical way, then either we cannot reject H0, which would be a correct conclusion, or we can reject H0, which would be a type 1 error. Okay, so type 1 is the most kind of obvious contradiction. We know it's true, but then we reject it nonetheless. So that is obviously false. You know it's true, but then you reject it. So that's a type 1 error. Now, I should say this. We as researchers can never actually know whether something is 100% true or not. So what this table is saying is that somehow, there is always, whether we know it or not, a reality, which is that either the null hypothesis is true or it's not true. We can never know what that reality actually is, but we know that there is an actual answer there. And so this table is set up in the way that even though we don't know what reality is, we know that there is a reality, and that reality is either H0 is true or H1 is true. Just like, think about the example we'll use is, one example is drug efficacy, right? So you can, disease testing. You can get a test to test whether you have a certain illness, and that test can either give you it can either tell you have the disease or not have the disease. But there's a possibility that it tells you have the disease when you don't actually have the disease, and there's a possibility that it tells you don't have the disease when you do actually have the disease. Now, you can't know necessarily in truth whether you have it or not. You're using the test to verify or to test whether you have it or not. But the results of that test could give you an incorrect result. So that's sort of the way to think about this. When we say H0 is true, this is you actually have the disease, even though you can't know for sure, or you actually don't, even though you can't know for sure, right? Okay, so reality, H0 is true. Either we fail to reject it, which would be correct, or we reject it, which would be a type 1 error. Alternatively, we could have the alternative hypothesis be true, in which case it's true, which would imply that H0 is actually not true, but nevertheless, we don't reject H0. So even though we know the alternative is true, we fail to reject it, and this would be what we call a type 2 error. Conversely, we could say H1 is true, but we reject the null hypothesis, which makes sense, and that would be a correct conclusion. I know that was sort of I did a not the best job explaining that. So let me try to make this a little bit clearer. So type 1 error. What is a type 1 error? It's a false negative. Think about a test for a certain sickness. COVID's a perfect example. You go get a COVID test. The COVID test tells you that you don't have COVID, even though you actually do, right? That would be what we call a false negative. That's a type 1 error. When the test tells you you don't have it, even though you do have it, false negative. The the other common example is, a jury case or a criminal case. Why am I being so dumb? A trial. And at the end of the trial, the jury has to determine whether a person is innocent or guilty, right? So the jury never tells you that you're innocent. They just tell you that you're not guilty. So the idea here is that a type 1 error is you're innocent, but you're found to be guilty, right? In truth, you did not commit the crime, but the jury still says that the evidence seems to indicate that you are guilty of the crime. That's a type 1 error. Type 2 error is a false positive, or maybe it's better to say a false not negative, which is a little bit different than a positive. This would be similar to you're actually guilty of the crime, but you're found to be not guilty, right? So here, the jury is not telling you that you're innocent. The jury is just saying the evidence doesn't seem to suggest that you committed the crime, but you could have actually committed the crime. So all we can say is you're not guilty according to the evidence, not that you're innocent. So type 2 error is like a false positive, or maybe better said, a false not negative. Because we're not saying that you are guilty. We're not saying that you are innocent. We're saying you're not guilty. So these are two types of errors that are unavoidable when you are testing hypotheses. You could commit either one of these types of errors. Now, that being said, you can control how much error you're willing to allow. And that's controlled using this alpha and beta value. So the alpha value is the probability of making a type 1 error. This is actually something that we set up as researchers. We can say we want to design the experiment in such a way that the probability of making a type 1 error is very low. We can do that. We can control alpha. Now, beta is the corresponding probability of making a type 2 error. And here's the tricky part. Alpha and beta go hand in hand. So if we design an experiment to decrease the likelihood that we commit a type 1 error, then we inadvertently and unavoidably increase the likelihood of making a type 2 error. So alpha and beta go, as alpha goes up, beta goes down, and as beta goes up, alpha goes down. Similarly, we could design an experiment to reduce the amount of type 2 error, but then we would inadvertently and unavoidably increase the probability of committing a type 1 error. So I know the type 1, type 2 error thing is kind of laborious and tricky, and other than a few questions that you'll be asked about it, it doesn't come up that much, but it's something to always bear in mind. When we're dealing with probability, when we're dealing with statistics, we can never make absolutely certain statements. There's always some degree of error. And here we're breaking down the types of error that you could have. You can either have a type 1 or a type 2 error. You have some control over how much error you will allow into an experiment, but as you control one, the other one inadvertently but unavoidably goes up. Okay, so enough of that. So finally, let's put it all together, and let me show you how this will actually look for you guys. Trying to fit this all on the screen. Bear with me. I'll zoom in as needed, but I want to go over an example. Hold on. Having camera difficulties here. Okay, so I'm going to go over this example and then use this flow chart that you see below to show you how you navigate reaching a valid conclusion based on the results of your hypothesis test. So let me make this clear. I haven't actually showed you yet how to do a hypothesis test. That's what the next sections will be all about. But you need to understand you need to understand how to make valid conclusions after you understand how to do the mathematics. So this is what it would look like. Researchers claim that P, some parameter proportion, population proportion parameter P is greater than 0.02. Okay, so notice that the researchers are claiming something. They can only claim one thing. What are they claiming in this case? They're claiming that P is greater than 0.02. So who are they claiming? They are claiming that H1 is true, because whenever you have a strict inequality, that's always an H1. This is also a one-tailed test. You can see, whenever you have the inequality, you have a one-tailed test. Okay, it's a right-tailed for what it's worth. Anyways, researchers claim P is greater than 0.02. Evidence suggests, so after we do the mathematics, we have two possibilities: either that we should reject the null hypothesis or not reject it. All right, so let me show you how to reach a conclusion based on these two outcomes. So this flow chart breaks it down. So we start, and the first question we have to ask ourselves is, does the original claim contain the condition of equality? So condition of equality, what do they mean by that? They mean, does the claim have an equal sign, or a less than or equal to, or a greater than or equals to? That's what they mean by condition of equality. So what was the claim in our case? The claim was P is greater than 0.02. So there's no equality here. No equality. So the answer is no, there is no equality, which means, as it's read here, the original claim does not contain equality. Therefore, the original claim is the alternative hypothesis, right? So really, you can read this more simply as, is the claim H0 or H1? Yes or no? So here, for our example, the claim is H1. That's what researchers think is true, not H0. Okay, so once we know who the claim is, then we go to the no branch. Now we do the mathematics and we reach one of two conclusions. The first conclusion is we reject the null hypothesis, right? So A is what happens if H0 is rejected. If H0 is rejected, then we say yes, and we take this branch, and then the wording of our conclusion is as follows. The sample data support the claim that blank, original claim. So for us, the original claim was that P is greater than 0.02. So that's the conclusion we can reach. We claim H1, then we fail to reject H0. No, sorry, then we reject H0. And since we reject the null hypothesis and we claimed H1 to be true, we then say the data seems to support our claim. Great. Now let's go the other route. So we're the same problem. We say, who are we claiming? Are we claiming H0 or H1? We claim H1, so we go this way. Then we get to this branch and we say, do we fail to reject or reject H0? In this case, for part B, we do not reject H0. So we fail to reject H0. And when we fail to reject H0 in this case, the wording of the conclusion is there is not sufficient sample evidence to support the claim that P is greater than 0.02. Okay, so what have we actually said here? We haven't said that our claim is false. We've simply said that we cannot rule out that H0 is true. So it's different. Just like I said, when the jury gives their verdict, they don't say you are innocent. They say you are not guilty. And the same is true here. We're not saying that the claim is wrong. We're just saying that that there's some probability, there's enough probability that the claim, the null hypothesis isn't wrong, so we can't actually reach a conclusion. So we're not, notice there's no actual conclusion being reached here. We're just saying there's not sufficient evidence to make a claim. We're not saying the other claim is true. We're just saying we can't say this one is true. So that's the way to flow through this. This flowchart is very useful. I will post it in the files on our Canvas page so you can print it out and use it to help you navigate coming to conclusions based on your hypothesis tests. You might get some practice with this in this section's homework, but you'll definitely be using it in the following sections. Okay, so that's section 11.1 or 10.1. It's all the vocabulary and the basic groundwork for hypothesis testing. This is actually the hardest part of it. If you can get a handle on the verbiage and how to reach these conclusions, then the mathematics isn't that bad, or at least it's nothing new. It's stuff that you've already seen. So we will see that in 10.2.